Well, thank you very much. It's a great pleasure to be back at the New Economic School. I've been to NES a number of times in the past, but never to this new building. The last time I was at NES, I think, was 5 or 6 years ago, and you were still in the old place. This seems better, so it's a pleasure to be here. And what I'd like to talk about today is some work that I have done actually over many years. So there's been an evolution with Drew Fudenberg on the connection between evolution and repeated games. A long time ago, actually about 25 years ago, to coincide with the anniversary, we published a paper on this topic, and we've been meaning to write a second paper ever since. I'm hoping that the second paper will be finished very soon, but let me tell you about our ideas as they currently stand. So you're, I'm sure, all familiar with the prisoner's dilemma, probably the most famous game in game theory, and it's the game on the screen. The prisoner's dilemma is important because it illustrates a potential conflict between individual optimization and group optimization. For the individual, in the prisoner's dilemma, it's always better to defect. The unique equilibrium is defect, but both players are better off if they cooperate. That's why the prisoner's dilemma is so interesting. Now, we know that in many settings, this conflict between individual and joint maximization can be resolved. And one important place where it can be resolved is when the game is repeated. So one important use that has been made of repeated games is to explain how individuals might come to cooperate even though in a one-shot game they would never cooperate. And because of its power to explain cooperation, repeated games have been used not just in economics, but in political science, in anthropology, even in biology. So repeated games are part of evolutionary biology. But there's a flaw to repeated game theory, which is that although in a repeated game cooperative behavior is possible, that is, under some circumstances, it will be an equilibrium for players to cooperate over time. It's always the case that uncooperative behavior is also in equilibrium. And in fact, there is a result in the theory of repeated games called the Folk theorem, which says that just about everything in between full cooperation and no cooperation can also be in equilibrium. So there's an enormous range of possible equilibrium outcomes. Theory seems to fail when it comes to making sharp predictions. There are too many possible outcomes. One possible resolution of this lack of predictive power might be to bring in evolutionary considerations. And when I use the word evolution, I might mean biological evolution, but it could be cultural evolution as well. Evolution, at least under some circumstances, may have the effect of promoting efficiency. And we might hope that evolutionary forces will weed out or kill off uncooperative behavior in the repeated prisoner's dilemma. This was a view that was expressed very forcefully nearly 30 years ago by the political scientist Robert Axelrod in a book called The Evolution of Cooperation. And let me explain the idea that Axelrod was putting forward. So let's imagine that there's a population of players. Think of them actually as a population of strategies. So imagine that players are programmed either by genetics or by their culture to play a repeated game in a particular way. Let's imagine that the general population initially consists of uncooperative players. So these are players who, when they play the repeated prisoner's dilemma, always defect. They always play D. Let's imagine that into this population we introduce a small population of mutants. Mutants are just players who do something that differs from what the general population does. Let's imagine that these mutants use what I'll call a conditionally cooperative strategy. That is, the mutant will play cooperate as long as its opponent has always cooperated in the past. But as soon as there's any deviation from cooperation, the mutants will play defect from that point on. So you cooperate if there's always been cooperation in the past, but otherwise you play defect. Now, how will this mutant population do once it's introduced into the general population? Well, let's imagine that from this mixed population, pairs of strategies are drawn at random and paired against each other to play the repeated prisoner's dilemma. And this is done over and over again. So there are lots and lots of random draws of pairs. And what we're interested in is the evolution of this population. Well, let's suppose that if a strategy does well over time, according to this random matching process, the fraction of the population corresponding to that strategy grows. So successful strategies grow in number, unsuccessful strategies die away. Well, how will conditional cooperate do? If it's matched against an always D player, conditional cooperates will do poorly for the first period because conditional cooperate will play C, always D will play D, so that means conditional cooperate will get a payoff of -1 in the first period. But then conditional cooperate from that point on will always play D, so its average payoff over the length of the repeated game will be close to 0, at least if the game is repeated long enough. So conditional cooperate against always D gets a payoff of essentially 0 on average against always D. Always D against always D also gets a payoff of 0 on average. But conditional cooperate against conditional cooperates will get a payoff of 2. Because if these two strategies are matched against one another, they will continue to cooperate indefinitely. So that means that on average, conditional cooperate does better against the population than always D does. Always D gets 0. Conditional cooperate gets 2 whenever it's paired against another conditional cooperate, gets 0 if it's paired against always D. So on average, it's doing better than 0. Conditional cooperates will therefore expand over time. That's the evolutionary part. Conditional cooperate is more successful on average than always D is. So conditional cooperate will expand as a fraction of the population. Or to put it in evolutionary terms, conditional cooperate will successfully invade a population of always D. And that means that this uncooperative behavior, the always D behavior, will in the long run be driven out. What I've just done is to explain fairly informally the idea that Axelrod was putting forward. I should say that I invite you to interrupt me at any time. If there's something that you don't follow, please ask. Don't keep silent, because if I lose you early on, you're not going to be able to follow what I say later. So don't suffer in silence. Let me know when you're not following. So this looks quite encouraging. Uncooperative behavior is ultimately driven out by this evolutionary sort of argument. And this kind of argument suggests that always D is not going to be evolutionarily stable. But there's a problem with this argument, and that problem can be illustrated by a slightly more complicated strategy, which I will call alt. Alt is also a repeated game strategy, and it does the following. Alt starts out by playing C. It plays C in the first period. It plays D in the second period, then goes back to C in the third period. It goes back and forth between C and D. It alternates, and it continues to alternate as long as both players have always conformed to this alternating pattern. But as soon as one of the two players breaks the pattern and fails to do whatever it was supposed to do in the current period, then alt plays D from that point on. So let's look at alt. Alt is not a very cooperative strategy. It only cooperates half the time. And that's before the pattern is broken. If you think about it for a minute, you'll see that there's no way that any strategy can invade a population consisting of alt. There's no way that a mutant can successfully invade a population of alt, because alt against itself, against another alt, is going to get a payoff of 1 on average. Half the time it'll get 2, half the time it'll get 0. That averages out to 1. If another strategy is going to have any chance at all of invading a population of alts, it's going to have to alternate too. If it doesn't alternate, it's going to get a payoff of 0 against alt, because alt reverts to always D if the alternating pattern is broken. So for a strategy to have any chance of invading alt, it's going to have to alternate as well. And that tells us that the alt cannot be invaded, because any potential invader has to behave just like alt anyway.
Can you please be more specific about what is invasion?
Invasion means a mutant invades a population if it does better on average than the general population. So starting from a population of alts, the best that a mutant can do is to get a payoff of 1 by alternating. If it does anything other than alternate, it's going to do terribly against alt. And so even against another mutant, the best the mutant can do is a payoff of 1. It can't do better than 1. So there's no way that a mutant can invade a population of alt. So now we're in trouble once again. It looks as though a strategy like alt, even though it's not very cooperative, is evolutionarily stable. And in fact, the situation is even worse than alt would suggest. Alt at least is cooperative half the time. Half the time it plays C, half the time it plays D. But imagine a variation on alt which cooperates a third of the time, and the other 2/3 of the time it plays D. For exactly the same reason that alt is evolutionarily stable, this even less cooperative cooperative strategy is also evolutionarily stable. And in fact, we can get arbitrarily close to completely uncooperative behavior while still maintaining evolutionary stability. So now, after the potentially optimistic message that Axelrod was giving, we're back in the pessimism of the folk theorem, which says that almost any kind of behavior can be in equilibrium. Almost any kind of behavior can be evolutionarily stable. Still, there's a sense in which this message is too pessimistic, because when you think about alts, you realize that it's a very inflexible strategy. What alt does, remember, is to alternate in this perfectly predictable way, and any deviation from this alternating pattern is punished by D forever. That kind of strategy will work well if there are never mistakes, if there are never misunderstandings. But let's imagine that we're in a world where, at least with some small probability, strategies do not get perfectly executed. So I might be intending to play alt, but occasionally I do the wrong thing. You know, machines, even very well-designed machines, occasionally malfunction and do something that they're not supposed to do. So let's suppose there's a small probability of execution. What I want to argue is that in that kind of world, where mistakes occur with small but positive probability, alt is no longer evolutionarily stable. So here's the argument. We start with a population where everybody is playing alt. We introduce a small mutant population, and the mutants are playing the following kind of strategy. As long as the alternating pattern is maintained, C, D, C, D, this mutant strategy, which I'll call S prime, alternates. But if there's ever a deviation from the alternating pattern, what S prime does is not immediately to play D forever, but instead to give the other player another chance. What S prime will do is, for one period after the pattern is broken, S prime will cooperate. In a sense, S prime is saying to the other player, I'm willing to overlook the broken alternating pattern what I would like to do is to cooperate. So S prime signals its intention. I put intention in quotation marks because, of course, these are just programs. They're not humans. They're either computer programs or they're genetic programs. But in effect, S prime says I'm intending to cooperate. If the other player, if the other strategy also plays C, then from that point on, S prime cooperates forever. But if the other strategy fails to play C in the period after the pattern is broken, S prime will play D forever. Now, how will S prime do in a population where most of the other players are alt, but some of them are other S primes? Well, if S prime is up against alt, it does the same as alt. It will get a payoff of 1 as long as the pattern is maintained. Of course, there's always a positive probability that the pattern will be broken. And at that point, S prime will get 0 and alt will get 0 if they're playing against each other. But S prime against another S prime is going to get a payoff of 2 after the pattern is broken. And remember, the pattern will be broken with positive probability because we're assuming mistakes occur with positive probability. S prime against another S prime will get a payoff of 2 because they will both cooperate after the pattern is broken. But alt against S prime is going to get a payoff of 0 after the pattern is broken. And so on average, S prime is going to do better against this population than alt will. So S prime will invade. What I've just shown you is the basic idea in this paper, which is that if there is a small probability of mistakes, then very uncooperative behavior like alt is likely not to be evolutionarily stable. Now what I've just done is to describe the results a little bit too crudely. It's not quite as simple as that. And what I want to do from this point on is to give you a framework which allows me to state the results more carefully and more accurately. But before I get to the model and the results, let me pause here for a moment and see whether there are any questions about the informal idea. Yeah.
Yes, I have a question. Do we assume that there is a probability of mistake in a period that follows the break of the pattern?
There's a probability of mistake in every period. Yeah. I will be laying that out more carefully in a moment. Any other questions? Okay, so let me describe the main results, and these results are going to be not just for the repeated prisoner's dilemma, but for any two-player symmetric repeated game. And the first result is that if a strategy is evolutionarily stable, and if players are not discounting the future too heavily, and if the probability of mistake is positive but not too high, then there's a sense in which the strategy has to lead to efficient, high payoff outcomes. So this is not quite right. I've got efficient in quotation marks, but I will explain what I mean by efficient in quotation marks in a few minutes. So that's one of the main results, and the other one is the converse. What I'm going to show is that if payoffs are efficient, then there must be some evolutionarily stable strategy which attains those payoffs, or at least attains those payoffs approximately, provided that there's not too much discounting, and provided that the mistake probability is small. Now, for the second result, we need not only for the probability of mistake to be small, but it actually has to be small relative to the discount rate. And that's a point that I hope to come back to at the end of the talk. So I want to set up a model which allows us to obtain these two results. And here is the model. We're going to be repeating a game G, which is a finite symmetric two-player game. By symmetric, I just mean that if we interchange the strategies of the two players, then we interchange the payoffs. And I'm going to normalize payoffs so that the minimax payoff for each player is 0. And we'll let V star be the set of feasible payoffs. So these are convex combinations of the outcomes of the game. Since we're looking at repeated games, we can convexify payoffs over time. So it's the convex hull of the feasible payoffs which are relevant. Now I'm going to introduce a non-standard definition. We'll call a pair of payoffs strongly efficient if not only are those payoffs Pareto efficient, they can't be Pareto dominated, but they actually maximize the sum of the two players' payoffs. So those are strongly efficient payoffs. So for the repeated prisoner's dilemma, there is a unique strongly efficient payoff pair, 2, 2. 3 minus 1 is Pareto efficient, but it's not strongly efficient because the sum of the payoffs is 2, whereas for 2, 2, the sum of the payoffs is 4. So for the prisoner's dilemma, there's a unique strongly efficient pair, but for this second game, which some of you may recognize as another famous game, it's called the Battle of the Sexes. In the Battle of the Sexes, there's a continuum of strongly efficient payoffs. Any convex combination of 2, 1 and 1, 2 is strongly efficient. And it turns out, and this will be one of the major points that I'll be making again toward the end of the talk, that this difference between the prisoner's dilemma and the Battle of the Sexes is very important. It turns out that the set of evolutionary outcomes, evolutionarily stable outcomes, is very different for the prisoner's dilemma than it is for the Battle of the Sexes. So when we repeat a game, we'll suppose that the game is repeated infinitely many times. That's just to avoid the fact that a finitely repeated game is non-stationary. It looks different once the game is begun than it does from the beginning of the game. An infinitely repeated game looks the same at any point. Just a little bit of notation. At any time t, the history of the game just consists of the actions, the pairs of actions that have been taken up to the previous period. And a history H can be, we can look at the mirror image of a history H by interchanging the actions. So pi of H is the same history as H, except that now we've given player 2's actions to player 1 and player 1's actions to player 2. And a repeated game strategy is just a mapping from histories to actions. Actually, more accurately, a repeated game strategy is a mapping from histories to randomizations over actions, but for convenience, I'm not going to worry about randomizations today. All of the repeated game strategies will be pure strategies. I am going to assume that all strategies are finitely complex, which, roughly speaking, means that they could be played by a finite computer. That is, the repeated game strategy can only remember a finite number of different histories. It can't be contingent on infinitely many different pasts. Yes.
How do we manage to accomplish that if we have an infinite game? I mean, after n periods, our memory will run out and our computer will fail.
Think of the strategy conditionally cooperate, where you cooperate as long as players have cooperated in the past. That's a finitely complex strategy. You only have to remember one thing about the past, whether people have always cooperated or not. If you think about it, most repeated game strategies that we talk about are finitely complex. So there's no problem. An infinitely complex strategy is a strategy that we almost never consider in repeated game theory. Virtually every strategy we talk about is finitely complex. That doesn't mean that we only look back n periods. We might look back more than n periods, but we only remember a finite number of things. We're also going to be supposing that in every period there's a small but positive probability that a strategy is executed incorrectly. The strategy, if the history of the game up to that point is H, then the strategy is supposed to play SI of H in the current period, but it plays some other action instead. We'll suppose that all mistakes are equally probable, just for convenience. And we'll also suppose that mistakes for different players are independent. So if I make a mistake, that doesn't make it any more or less likely that you will make a mistake. Okay, so this expression looks like a mess, but it's not something that you have to worry about. All we're doing here is looking at the this is just a formal statement of the expected payoff that player one gets. The first line is the expected payoff that player one gets if players are using strategies S1 and S2, and there's a probability of mistake P in every period, and the discount rate is R. So all I've done is to compute the discounted payoff that player one gets from those strategies given the mistake probability P. And this second line is the same expression, except that we've now made those payoffs contingent on, or conditional on history H. So starting from history H, what is player one's expected discounted payoff? These are actually discounted average payoffs, so we're looking at what player one would get on average in a single period. Now we have to talk about evolutionary stability. So in the introduction, I was suggesting that a strategy is evolutionarily stable if it cannot be invaded by a mutant, S prime, the formal statement of this is that a strategy S is evolutionarily stable with respect to the parameters Q bar, R, and P. Remember, R is the discount rate, P is the mistake probability. If for any mutant S prime, strategy S against the population of S and S prime does better on average than the mutants S prime does against this population. So think of Q here as being the probability or the proportion of the population corresponding to the mutants. So there's some upper bound, Q bar, on how big the mutant population is. And 1 minus Q, the remaining proportion of the population, corresponds to the dominant strategy, the strategy S. This expression here is just the expected payoff that strategy S gets against this population, where a proportion Q corresponds to the mutants and a proportion 1 minus Q corresponds to S. So this is the payoff to S against this mixed population, and this expression is the payoff to the mutants against the population, and S prime fails to invade if the expected payoff for S prime is lower than the expected payoff for S. So if this inequality holds for all mutants S prime and all proportions Q of a mutant population less than some upper bound Q bar, we say that S is evolutionarily stable. It cannot be invaded by any mutant. Now this is a static concept of evolutionary stability, because we're not talking about the dynamical process by which the mutant either grows versus the general population or dies away versus the general population. Part of the paper actually shows that this static concept of evolutionary stability can be given dynamical content, but for our purposes today, I will ignore the dynamical side. So let me skip over the dynamics and get to the first main result. So the first main result is actually labeled Theorem 2 because there's another result having to do with dynamics, which I'm ignoring. So let V lower bar be the lowest payoff that is consistent with strong efficiency. So I should explain that for the prisoner's dilemma, where there's a unique, strongly efficient outcome, V lower bar is just 2. That 2 is the lowest payoff consistent with strong efficiency. If there's just one strongly efficient payoff pair 2, 2. But for the repeated battle of the sexes, V lower bar is 1, because 1, 2, payoffs 1, 2 are strongly efficient. So 1 is the smallest payoff consistent with strong efficiency in the repeated battle of the sexes. So the first formal result says that if a strategy is evolutionarily stable with respect to Q bar, R, and P, and if R and P are sufficiently small, then the payoff corresponding to strategy S cannot be very far below V lower bar. So that this is making formal the idea that if strategies are evolutionarily stable, they can't be terribly inefficient. So that means that in the repeated prisoner's dilemma, if a strategy is evolutionarily stable, it must deliver a payoff close to 2 on average. For the repeated battle of the sexes, an evolutionarily stable strategy must deliver a payoff close to 1 on average. So not necessarily very efficient, because we could have payoffs 1, 1, for example, in an evolutionarily stable configuration, but at least there's a lower bound which is above 0. Okay, so how do we prove this result? Well, it's actually very similar. It's very similar to the proof that I gave that showed that alt is not evolutionarily stable. The idea is that if S generates a payoff that is below V lower bar, we can construct a mutant which will successfully invade. Now, how do we do that? Well, the problem that mutants face is how does S prime avoid getting punished by S if it deviates from what S does? That's not completely avoidable, but what S prime can do is to make sure that it behaves exactly like S unless the worst has already happened. By the worst already happening, I mean that we have already got to a history H star in which the future payoff from S is minimized. Remember, because mistakes are occurring with positive probability, any history H star is possible. Any history has positive probability. Let's look at a history for which the future payoff corresponding to S is minimized. Then H star is, in effect, the worst possible history that can occur. that's a very good place for a mutant to try to invade, because you can't, S was already going to be getting a low payoff. The worst that can happen to S prime is it can deviate from what S is doing, but it can in effect only be punished for one period, because the worst that can happen after that deviation by S prime is that the history following H star can be restarted. So here's what S prime does. S prime behaves exactly like S, except after H star, or the mirror image of H star. After H star, S prime deviates from S. It signals its willingness to cooperate by doing something different from S for one period. If the other player responds in kind, then S prime plays strongly efficiently from that point on, and otherwise S prime goes back to doing what S did. And because H star is already the worst history, by playing in this different way, S prime can lose out, if it's playing S, only for one period. Because the worst that can happen is that S will do, after this one period deviation, what it was already doing after H star. So that means that S prime is going to do nearly as well against S as S does against S. Just this one period difference. And S prime against S prime is going to do very well indeed after H star. It's going to get a strongly efficient payoff. So on average, S prime is going to do better against a population consisting of S and S prime than S does against that population. In other words, S prime will successfully invade. And here we're making use of the fact that we're assuming that S is not strongly efficient when we construct the deviation by S prime. If S is not strongly efficient, that means that S prime against another S prime can do strictly better against another S prime, and that means that on average S prime must be doing better against the mixed population than S is. So that's our first result. And that implies for the prisoner's dilemma that if a strategy is evolutionarily stable and the discount rate and mistake probability are small, we must be close to cooperation. But the same thing is not true for the battle of the sexes. Let me show you. Let me jump ahead and show you what happens when this game is repeated. This is similar to the battle of the sexes. So these four squares here are the battle of the sexes, but I've added on another. Well, I've added two strategies, C and D. It's really D that is the important one here, leading to payoffs 2-2. Now, payoffs 2-2 are not strongly efficient. 2-2 adds up to 4. The strongly efficient payoffs are these, 1-4 and 4-1, and convex combinations. But nevertheless, we can get payoffs 2-2 in an evolutionarily stable way. And here's how. So let's look at a strategy which plays D as long as in all previous periods both players have played D. But if one of the players fails to play D, then that player is punished. Let's suppose it's player 1 who deviates. Then from that point on, we go to 1-4. If, on the other hand, it's player 2 who deviates, we go to 4-1. Now, what I've just described is evolutionarily stable. Even though it's inefficient. It's evolutionarily stable because the punishment itself, 1-4 or 4-1, is strongly efficient. Notice that when we previously showed that that inefficient strategies were invadable by mutants, those mutants exploited the fact that the punishment itself was inefficient. When we showed that alt could be invaded by S prime took advantage of the fact that alt was always playing D after deviations, and that playing D is very inefficient. But this strategy, after deviations, plays strongly efficiently. There's no way that a mutant can get a toehold. There's no way that a mutant can take advantage of the inefficiency of the dominant strategy because there's no inefficiency on the punishment path. And so that is the explanation for why, with the battle of the sexes, it's possible to have inefficient payoffs which are evolutionarily stable. As long as the inefficient payoffs are sustained by punishments which themselves are efficient, there is no way that the mutant can exploit the dominant population. The punishments here are directed specifically to the player who deviated. This is the punishment for player 1. This is the punishment against player 2. But in the prisoner's dilemma, it's impossible to punish players efficiently or strongly efficiently. And so in the prisoner's dilemma, we cannot avoid having we cannot avoid having mutants invade if a strategy is sufficiently uncooperative. Now, when I was talking about Axelrod's work, I was talking about conditional cooperate. Remember, conditional cooperate is the strategy which plays C as long as there have been no deviations previously, and plays D after some deviation. That kind of strategy is not going to be evolutionarily stable because the punishment is extremely inefficient. Always play D. Let me show you let me show you a strategy which is evolutionarily stable. And it's this. So, suppose that suppose we look at a strategy which starts out cooperating and continues to cooperate as long as both players played C the previous period, or both players played D the previous period. That's a strategy in which punishments will last for exactly one period. Suppose we're cooperating and for some reason, say I made a mistake, I play D one period. Well, that will have to be punished. In the next period, we will both play D according to this strategy. So I will be punished for one period. But then in the period after that, we'll go back to cooperating again. So this is a strategy in which, yes, there are punishments, but the punishments last for as brief a time as possible. They last for just a single period. And so, although punishments are not strongly efficient, they're as close to being strongly efficient as you can get. And you can show that if the probability of mistake is small and if the discount rate is small, this sort of strategy actually is evolutionarily stable. It's not quite strongly efficient, but it's close enough so that it cannot be invaded by any mutants. Let me make one more point. I said that in order to get the existence, well, actually, let me make 2 points, because I never actually stated Theorem 3. Let me state Theorem 3. So this is the converse to Theorem 2. Theorem 2 says that if a strategy is evolutionarily stable, then it must give us payoffs which don't depart from efficiency by too much. This theorem says that if payoffs don't depart from efficiency too much, then we can find evolutionarily stable strategies which give us these payoffs, at least approximately, provided that the discount rates and the mistake probability are small enough and that the discount rate is not too small relative to the mistake probability. So in other words, R and P both have to be small, but in some sense, P has to be even smaller than R. Let me show you what goes wrong if P is big relative to R. Okay. So think of the prisoner's dilemma, and think of the strategy that I was just telling you about, that is evolutionarily stable for the prisoner's dilemma, namely cooperates if both players cooperated last period, and also cooperate if both players defected last period and otherwise play D. That's a strategy which is sometimes called modified tit for tat. Now, if this strategy plays itself, then if there's no mistake, it will deliver a payoff of 2. But every time the strategy makes a mistake, there are going to be 2 kinds of losses. First, there'll be a loss in the period where the deviation occurred. In the period of the deviation, one of the players is getting 3, one of the other player is getting -1. If there had been no mistake, they both would have been getting a payoff of 2. So the loss is just the difference between 2 and the average payoff that a player gets when a mistake occurs. With 1/2 probability, the player gets 3 if he's the one who made the mistake, and with 1/2 probability, he gets -1 if it's the other player who made the mistake. And so the difference between no mistake and a mistake in the period where the mistake occurs is 1. But then there's an additional loss that comes from the fact that in the following period there's a punishment, and both players are getting 0 in the second period, whereas if there had been no mistake, they would have got 2. So each mistake leads to a total loss of 3, the probability of a mistake is p, and then we have to add up the losses over time. This expression here is the expected discounted loss from mistakes if modified tit-for-tat plays itself. Now let's imagine a mutant strategy which doesn't punish. So it does everything that modified tit-for-tat does, except that if a mistake occurs, there's no punishment. Instead, what S prime does is to go back to cooperating again. Well, that strategy against itself is only going to incur the loss from the first period, not the loss from the second period, because there's no punishment. So that strategy against itself is going to have a lower payoff from losses. And if R is small enough relative to P, the fact that there's a much smaller loss from punishment is going to be very important, because this expression is going to be very big for R small relative to P. And therefore, modified tit-for-tat will be invadable by a mutant strategy for R small relative to P. And that's why I was suggesting that for evolutionarily stable strategies to even exist, we need not only small discounting and small mistakes, but not we want the P parameter to be relatively small compared with R, which is a restriction on the on the parameter space. We cannot have evolutionary stability for all parameter values, but at least for parameter values where evolutionarily stable strategies exist, this point of view, this argument, tells us that we can expect evolution to push us not completely to efficiency. Certainly for the repeated battle of the sexes, we may still be quite far from efficiency, but at least for games like The Prisoner's Dilemma, where there's a unique, strongly efficient outcome, we are going to get pushed very close to full efficiency by evolutionary stability. So the original Axelrod insights was, roughly speaking, correct. His arguments had a flaw, and we showed that alt, which is a highly inefficient strategy, could be evolutionarily stable in the Axelrod sense, but once there's a positive probability of mistake, then highly inefficient strategies like alt are driven out by evolution, and the optimistic conclusion that Axelrod was suggesting is actually valid. But the lesson that we're trying to draw from this analysis is that it's very important for efficiency that there be mistakes. That may sound intuitively contradictory. How can mistakes lead to greater efficiency? But as you can see, without mistakes, very inefficient behavior can still be invadable. And that, we think, is the contribution of this paper. So let me stop there and thank you for your attention.
So I believe we do have some time for questions. So if anyone wants to have a go, by all means.
Sorry, can you speak up, please?
Yeah, on DNA, on mutation, in real life, we can think the rate of mutation being kind of proportional can be associated with probability of mistakes. And we know that some organisms, viruses in particular, and AIDS virus, that has an increased rate of mutation, and that itself makes it interesting, let's just say, out of scope. So can evolution be directly on the rate of mistakes? Or can we look at the evolution in double both on selecting what to play and on the actually developing the mechanism, generating mistakes? In fact.
So that's an interesting question. Could P itself be a parameter which evolves in a model like this? What this analysis? So this analysis is too crude because it's still essentially a static analysis to answer the question, what is the evolutionarily stable value of P? All this can tell us is that P is going to have to be positive and not too big. But beyond that, a purely static analysis can't pin down the numerical value of P. But if we went back to the part of the paper that I omitted, the dynamic part, then it would be possible to have P as an evolving parameter too. The evolutionarily stable value of P would be the one for which, if mistakes occur with probability P and there's some mutant that makes mistakes with some other probability, that mutant could not successfully invade. So yeah, this paper doesn't answer the question, but the question is answerable. Yeah.
In this proof, you said that for big P, this strategy is not stable, but maybe any other strategy can be stable. So we can't say that there is no strategy which is stable.
All right. So what I've done here, this is not meant to be a proof. This is supposed to be suggestive. In a sense, the modified tit for tat is if anything is going to be evolutionarily stable in the repeated prisoner's dilemma, modified tit for tat will be. Why? Because the strategies, the punishments are as short as possible. If a punishment is short, it's very hard for a mutant to invade. And so intuitively, if tit for tat can be invaded, then almost any other candidate for evolutionary stability can also be invaded. You're right, that's not a proof, but it's at least suggestive. And all this argument was meant to give us is the rough intuition for why P has to be small relative to R.
All right. Thank you very much.
Okay, thanks.